So thank you for the invitation and the opportunity to speak here. So I will talk about some new aspects of an old result, ergodic theory about Katz lemma, and this is based on, or at least the new parts are based on joint work with Benjamin Weiss. So, okay, so this is ergodic theory, the subject of this talk. So the setup is the following: we have a probability space. Okay, possibly coming from some space with additional structure. And we have a ergodic theory. So we have a transformation of the space, and it is measure preserving, probability preserving. So T star mu equals mu. And let's say ergodic for some of them. And now, what does Katz lemma say? So I will state it. Given a measurable set of positive measure, we look at the return time. We're point to set. So for a point in A, we look at Ra of x. It's the first return time to the set A. So it's the smallest non-negative integer such that t to the nx is again in A. Okay, so if this is our space X, and this is A, we have a point, X, move to T of X, and then at some point, the first time we return is T of Ra X. Okay, we traverse around the space. So what does Katz lemma say? Okay, I'll give the statement. It says that T is ergodic.
I think you forgot the int.
Oh, sorry. Yeah, of course. It's not a set, it's a number. Yes, the infinite. Yeah, it's the smallest type, minimum. And okay, right. This I should say this is the first return. For the point x. Okay, Katz lemma says that if t is ergodic, and UA is greater than 0, then the return time integrates to 1 over A, which if you want to normalize this to be a probability measure, it means that the expected return time, conditioned on the fact that you started at A, is equal to 1 over the probability of A. It's inversely proportional to the probability of A. This is extremely intuitive, very simple. Okay, how much time do you have to wait on average to return? Just depends on the probability in A, inversely proportional. No, but it is extremely useful, of course, this is, of course, this is by Markatz. So it's very determined to mention Polish mathematician this seminar, and now there are some subtle points here, of course, that if you start at an arbitrary random point in the space X, okay, so you choose your point randomly and you take expectation not over A but over X, the expected time to visit A, it's much more intricate and complex, right? For example, if you toss coins and you're looking for the first, you're waiting for a pattern of 4 heads or a pattern of head, tail, head, tail. The expected time it takes you it depends on the pattern in intricate ways, right? It's kind of an exercise. And but if you start at the time where the event occurs and you're looking for the next time, then it does not depend on the transformation, on the statistics, on autocorrelation. It does not, just on the set. Yes.
There is this lemma by Roglin, which gives the compositions of the spaces. Is it related to the height of the Roglin towers?
Well, this could also say that the expected height of the Rockling tower is 1 over the probability.
It's exactly that.
Yes, equivalent in this case. Right, so there are many formulations, and now kind of a basic question, which I'm sure has been asked well before, and I would not be extremely surprised if in some form it has been answered somewhere, but by now, for reasons that have to do with the content of this talk, I'm more and more convinced that it's the proportion of people who are aware of it previously is not so big. Okay, the sample a long list. So the question was, okay, let's state it informally, is there an analog, or in fact a generalization of Katz's lemma for for actions of general, more general. And let me write in bracket amenable groups. Okay, so here you have one transformation. If it's invertible, okay, invertibility is not needed for the statement of Katz's lemma, but it's also not so much a restriction to assume it. You can pass to the natural extension and deduce the non-invertible case from the invertible. So suppose you don't just have one transformation, but a group of transformations acting on probability space.
You assume discrete?
Yeah, so let's say, yeah, the question is not precisely asked in this way, and in this form it appeared, so I mean, kind of, one of the first time I gave this talk, after the paper is written, this was the motivation, I can search online for instances of where it appeared, and I find, I mean, one of the first things that comes up is the question by, it's exactly this formulation of the question, by Iterates. From 2015, it's not a paper, it's on a math overflow question. And then there are responses. So, for example, Uri replies and asks, okay, before considering general amenable groups, what is the formulation of this question? I mean, is there an analog for, the next simplest cases, which would be z squared or z times a finite group, like the group with 2 elements, or a finite group? I mean, these are all examples of a amenable group. Is there a meaningful analog extension of this for these situations? What does it mean? And there was something in mind, and then there was a reply, which I'll state. So Aronson and Weiss in a paper in 1923 had ZD partial element. Something called random, which is some kind of weakening Katz inequality for ZD. So there was some previous result. It was intended for particular application. So Katz lemma has many, so basic, it has many opening towers, it has many basic applications in ergodic theory. And when you want to obtain similar results for other group actions, for example, for ZD actions, then it's very useful to have something like this. And the result they were after was the existence or non-existence of ergodic theorems with large normalizing constants. So the question was something like this. If you have an L1 function, in an ergodic transformation, right, in the space for the ergodic transformation, and you look at the ergodic averages, then they converge almost everywhere. If you look at the question, a function which is too big to be in L1, it's not in L1, you might ask, maybe you don't normalize by 1 over n, by something bigger, and you recover the convergence, so it was proved that this is not possible ever in general extension. And the purpose of this paper was kind of to obtain the non-existence of large normalizing constants, and what they needed for, what sufficed for that was a kind of a weak version of Katz lemma, where the weakening was in two parts. First of all, this was not an equality, there was just some inequality here, and it was for a class of transformations that was sufficiently big, sufficiently big so that any ergodic transformation has an extension in this class, let's say briefly. Okay, so this is the background, and the purpose of what I would like to talk about is to formulate a relatively simple, this whole thing, I mean, if you look on archive, the whole preprint is 12 pages or something like that, very expository. The results are not intricate or technically difficult. It's just a matter more or less of formulating the concepts and finding the right formulation. So let me present a formulation which will fully extend this lemma of Katz. Discuss it. The setup now will be slightly more general. I will have gamma will be a countable. Okay, answering the question. And we have, instead of one transformation, we have an action of gamma, which we denote by T, on the probability space. So this is the probability preserving. In general, not assuming ergodicity for some formulations that we need. And so by this I mean, just in terms of notation, so if gamma is an element of the group, so T gamma is a probability preserving transformation, and composing to means applying the corresponding result for the product. So I'm using notation of left actions that Misha likes less, but so part of the problem is that there is no notion of time, so no first return time. We need a substitute for that. So the key concept, or one key concept, is the notion of so the key notion is the notion of an allocation. So I have a set A, so an A allocation will explain the name in a moment, is a measurable function let's use the letter kappa, from my space X to the group gamma. So for each element, I assign an element of the group such that, so how is it related to the set A? Such that if I take X and I apply the transformation T kappa of X on X, right, so the kappa tells me which element of the group to apply, I end up in the set A. Okay, so this is the key concept, and then, well, I'm in the measurable category, so almost surely. Okay, so it needs to be almost surely defined, everything. And the other thing that kind of justifies the name allocation is this thing. Given an A allocation kappa and an element X, I look at the set B kappa of X, which is, okay, it's a set now I'm not missing an int or anything. It's the set of elements in the group such that if I look at okay, so it's the set of elements gamma, such that if I look at X, I go to the place in the orbit corresponding to this element of the group, then kappa tells me, okay, to use this element. So let me explain what this means. Okay, this is a subset of gamma. Subset of gamma. So to each point X, given an allocation, I have a subset of gamma. Roughly speaking, let's say if the action was a free action, this would kind of tell me, so if the orbit of the group corresponds, the orbit of an element is a copy of the group, can be identified with a copy of the group, it would tell me which elements of the orbit get mapped to this point X. Okay?
So this really makes
So-
sense
so-
for X is in A, right?
Exactly. Yeah. So this is for X is in A. So this justifies the notion of allocation. To every element of A, I allocate some element in X. Okay, now, yeah. But kind of this is the formal way to state it, and there are some intricacies. I'm not assuming necessarily that the element is set. Yeah, right. So the element of gamma, exactly. If the action was free, then you could kind of use this correspondence between the orbits and the group, between an orbit and the group. And let me just to illustrate.
So in principle, you can get a variant of Katz's lemma also in the classical case if you
Right, exactly.
another allocation.
So let's just, many of you have caught this already, but just to kind of recover and recast this in the classical case, for example, if you take gamma equals z, and you take kappa of x, so you have z acting on probability space, and you take kappa of x to be the minimal n such that Tn of x is in A, right, which is exactly the return time. Then, okay, let's look at this. Then in this case, B kappa, okay, let's say that y is equal to Ra of x, right? This is the same as Ra. And let's say that y is equal to Ra of x, so let's look at what is B kappa of y. okay, the place where I return when I apply x, this will be exactly okay, so this is what happens. So what we have, so the conclusion is that the size in this case of B kappa, B kappa of T kappa x of x is exactly the return.
Sorry, why you are considering n positive and not the absolute value in your definition of KS here?
Sorry, what?
If you are considering gamma equals n, why you are not consider the negative n?
Yeah, so I mean, I have,
It's your choice.
I mean, this is an example for an
Okay.
allocation. There are many allocations that I can choose. Okay, this is a many, yeah, I can choose, right, the closest. But I'm saying that the return time can be interpreted in this, as the size of this kappa,
Small x.
of the size of this set, okay, in terms of allocation. And the reason I'm giving this interpretation is to formulate the following theorem. So here is the theorem.
In your definition, you had T kappa minus 1 of x. And here you have T kappa in the example.
No, because this is a B kappa of y, where y is,
Oh, okay.
right? Sorry, y is, yeah, I missed it. Y is T of R of x, right? It's T kappa. Yeah, y is where you return.
Okay.
So this is the formulation. So it is consistent with this. And so here is the formulation of a theorem that generalized lemma. So it says the following thing, that kappa be an A allocation. Okay, so we have this set up, right? And F here, just not to state anything about integrability or something, that you have a non-negative measurable function, and of course, you know, when you have things absolutely convergent, you can test integrable, a non-positive function or complex or whatever. So I'm defining a new function, f kappa. F kappa of x, for x in A, is equal to sum over gamma in B kappa of x. Okay, summing over all the gammas that are somehow associated to this point x by this application. F T gamma of x. Okay, so this is a definition. I'm defining a new function. Somehow I have kind of an operator maybe on acting on spaces of measurable functions. And the conclusion is that the integral over A f kappa is equal to the integral over x of f. And let me just say what this means in particular. So this is an identity. So I mean, I have a function using the allocation and define a new function defined on A. And the integral of the new function on A is equal to the integral of the old function on x. So just, I mean, why do I call, this is kind of a generalized Katz's lemma. Why is this a generalized Katz's lemma? So for the following reason, in particular, take f equal 1, the identity function 1, you get that the integral over a of, so what is f kappa? It's just the sum, it's just the number of elements. Okay, and this is equal to 1. And, you know, if we look at this example, then this is just saying, you know, for the case of this example, it recovers Katz's lemma. Okay. Now, okay, there is one thing here that I said, that here I said probability preserving, and here I define this. Now, for this to be well defined, it's not enough for A to be a set of positive measure and for the transformation to be probability preserving. You need any point in X, the orbit of any point in X to intersect the set A, which is something you call, I mean, this property of a set is sometimes called to say that A is a sweep out set. I mean, the union over translates of A is essentially all the space up to measure 0. So for ergodic transformation, every set of positive ergodic transformations precisely is those for which every set of positive measure is a sweep out set. So this is the relation. This formulation does not involve anything. Now there are some components here that are okay. So this, let's say, call this theorem 1 for a statement. Okay, now let me say a few more. So I would like to kind of say a few words and then kind of reformulate this and say, give it another angle or two for this theorem.
What does it mean, for example, for z squared?
So what does it mean for z squared? Okay, let's go exactly to that. So now, let me kind of expand a little bit on what happened in this work of Aronson and Weiss from the 90s. Okay. So, exactly this. So this is 23, and the paper is called something. Okay, so the title, as I explained, is for the application. Ended up, so it's a ZD ergodic theorem with large this is kind of telling you what was the application to ask. And the definition that the setup was that you had okay. So this is an ergodic transformation, and again a measurable set of positive measure. And then they defined something called a Katz function. So a Katz function is a measurable function from A to the integers such that, so two things happen, it satisfies two properties. So it tells you for every point of A, how far do you need to go out, sort of, to do two things? Such that, okay, so two things happen. I will write the formula concisely and then I will draw a picture to say what it is. The first thing is that the space X up to measure 0 is the union over N, the union over V in Bn, I would say. Now Bn is the box of size n, centered around the origin. Well, not of size, but
In the group,
in the group, yeah, I will say it in a moment, in ZD. So Bn is equal to minus n. Right, this is a subset of Z. And so this is what happens, and I will say in a moment. The whole space, okay, it can be viewed as a, yeah, it's a free ergodic. And the second thing is that, so that's one thing. Okay, I'm sorry, I will continue forward. That's one property, and the second, so I will say, I will draw a picture in a minute to explain what this formula means. And the second property means that if you on A, the expected size of a box of size phi of x is finite. So let me explain what this means. So I have, let's say I have, a point x and x, and I have z squared. And let's say I draw an x. This is, the x's are the sets that, okay, let's not set this. Let's do this a different way. This means that, right, these are all kind of v. These are all the times when t is in A. Okay, I look at the orbit of the point x and I look at the elements of the group that I apply to be in A. So for each of these times, I put a box of size phi. Okay, this function phi tells me how big needs to be a box around this. And this formula, so there are different size boxes for, this formula says that almost surely if I put a box of this size, phi of x, phi of t, b of x, around each of these points, it will cover ZD. Okay, not disjointly cover, but cover. So the first property says that the boxes, okay, it tells you at each point in A how big the box needs to be. The first property says I cover all the orbits, almost surely. The second property says the boxes are not too big on average, in the sense that the expected volume of the box has finite expectation. And the result of Aronson and Weiss was that for certain types of ergodic transformations, namely, if you take an arbitrary ergodic transformation and multiply it by the adic odometer, this is one specific information, a cut function exists. And moreover, if you look at the proof, which is explicitly done for z squared and extendable to zd, then it's not only finite, but you get an explicit constant here, depending on the dimension d, like maybe 36 for d equal 2, that was done before, not depending on the transformation or the set A or anything else. Okay? Just for illustration, if you go back to Katz's lemma for z, so not only is it finite, I'm saying, if you actually look at the proof, then it tells you that, so the random Katz's lemma, that they have says that for a certain class of ergodic transformation, namely taking product of certain class of probability transformation, namely those which come from taking product with the adequate odometer, cut function exists, and moreover, not only is this finite, but it's less than 36. Less than some explicit universal constant depending on d, but not on anything.
And this B is the B that was used before.
No, well, it's kind of related, but it's a different notation. This B. Sorry, what is this? No, this B. This B is like I define Bn. Bn is just a box of. This is just like this expression is just 2n to the d. Phi n, phi of x to the d. This is actually what this is, right? It's the box of side length phi of x. Phi of x is an integer. This is,
Can you look at it like you subdivide A into subsets an, out of remaining subsets, stated that union over n of all shifts of an by elements from Bn is the whole x, and that this formula would be just a sum of 2n power k of measure of an is finite, something like that.
this would say, yeah, this would, I mean, yeah, this would say that the sets, I mean, if these sets are not disjoint, right? So it says something about the sum of the measures of those sets being finite. Yes. If they were, so again, let's just look. If you look at if I did this for z, and for each element of A, I would look at you know, how far, what is the minimum of the absolute value of n, such that t to the n is in A. In other words, if I look at every point, I look at the point in x, and I look at the times where it is in A, and for each time where it's in A, I look at the smallest interval, centered interval, such that it is, sorry, I look at the, yeah, I would need to do something else. I look at maybe the largest interval such that not both endpoints have passed another point. Okay, so that then in that, okay, that's what the minimum that you need to cover by centered intervals. And in this case, so what would happen, right? I would have z, and I would have some subset of z, and for each point, you know, I look at, you know, maybe here we have to go to here. So if I go here, I look at the centered interval, the smallest centered interval that makes sure I reach this one. Maybe I can do that. If I do this, then what would happen is that I would cover the orbit, and the multiplicity would be bounded. So I would get this with a constant of 2. Right, so this is the Katz lemma, and let me, so the previous theorem, let me reformulate it and say what you can get in these terms. So similarly, you could define a Katz lemma for other group functions. A Katz function. So here is a reformulation, almost reformulation, not quite. Needs a little more of the previous result. It says so now we have gamma acting. preserving any, and A a sweep out. So this means that x is equal to up to measure 0. Then there exists D1, D2 subsets of gamma finite, sequence of finite subsets of the group. Okay, so these are the n, and a function from A to n. So this is my Katz function, such that this two things happen. First of all, x is the disjoint union. Same thing as here of okay, so in the case of a free action, what it means is, for every, there's a function, a sequence of elements of the group, a function that tells me to any element of A, which group element to assign, and then if I take a point X, okay, let's say the action was free, so I take an orbit, and I put around each point of the orbit a translate of the element that the function tells me to take, then it tiles the orbit, disjointly covered, and then 2, as a consequence, what I get is that the integral over A of the element B phi of x, right? I have B by to Bn, phi of x is an integer, I tell you which element of the sequence. The size of this, not only is it finite, but it has measure 1. Okay, so this is the formulation, and it's a little intricate, actually, it's cheating. It's like putting this formulation so that it's in line with this statement. And let me just stress something. This is not a strict strengthening of this result, although it does strengthen various aspects of it. Okay, for example, arbitrary group, disjointly tiling, not just covering, and having an optimal constant of 1, but there's also a substantial weakening in the sense that these sets, Bn here, they're just centered boxes, and here there are arbitrary sets. Now, if you restrict to ZD, they don't need to be so arbitrary. They can be essentially convex sets in the sense that any point in the interior of the convex hull is contained in the set by basically taking the Voronoi diagram of a point set in ZD associated with visit times 2A.
Because in particular this formulation tells you that these sets depend on the choice of the action.
Okay, so actually, I wrote it like this just not to make it involved, but in fact, right, the sets just depends on the group, and you can say for something about them for a nice group. So, for example, for ZD, you can take almost convex sets. You can, I think it's impossible to get with the optimal constant 1 centered boxes. It might be possible, I'm not sure, to take non-centered boxes, but containing the elements.
Sorry. So,
Yes.
So there is no assumption on the finite subsets. So they should cover the group.
Sorry? Well, okay, of course. Here it says it doesn't say for any sequence of subfinite. I mean, yeah. Let's put it this way.
There exists a sequence with some other properties of just a sequence of finite.
Yeah. Okay. So here when I formatted, I said there exists a format which is equivalent to saying, right? I mean, actually, it's cheating. It's just to say I could have taken the sequence to be an exhaustion of the finite subsets of the group, right? So there's nothing like this. But in fact, if you look at it, you can say more. So, for example, for ZD, you can take these to be convex or essentially convex, right? In this sense.
Increasing.
Yeah. No, not increasing. Not increasing with it. Because, I mean, or at least I don't see, I mean, yeah. So there is, this is a very soft result that there is improvement. I don't know that increasing. For example, can you take them to be, yeah, increasing, I'm not sure. I kind of doubt with this concept. Yeah. I mean, not possible for some things. I doubt it in this generality, at least. That they are increasing. But for example, you know, Fellner or something, so convex subsets are Fellner indices. So it's good for some applications. Okay, so I just about to conclude. Let me mention one more formulation, and let me say, so of course, somehow this thing, it's not, I mean, definitely in retrospect it looks like something that should not be new, right? But I kind of try to look about for where, or try to look for what was known. And the closest kind of concept that appears is really closely related. The concept in probability theory, I mean, comes from other places, but they kind of used in the probability theory by probably studying, for example, random graphs and things like that. And it's the notion of the mass transport principle. So it's closely related. Somehow the mass transport principle can in some sense be recovered from a formulation of this, and possibly vice versa. Of course, the proof in the end is very simple and very short, so there's not too much in there. But let me just give one more formulation, which is simple and somehow it's the simplest in the sense that it's the least non-standard definitions that you need, like allocations or something like that. All you need to know is a concept which is a little intricate but very classical, which is probability preserving equivalence relations. So this is Kat's lemma for probability preserving equivalence relations. So the setup is the following, and I'll conclude with that. We'll definitely not go over time in another talk here. Let X d mu be a probability space. Let's say standard. By which I mean that I think that X B is the standard Borel space and mu is the Borel probability measure, and R mu preserving countable equivalence relation. So this is the concept that's been developed in around 50 years ago, at least, by the work of Feldman and Moore. What it means is that R, let's say, is a Borel subset of this, that for every point, a Borel subset which is an equivalence relation, for every point in X, the equivalence class is at most countable. So this is the countable. It doesn't mean that R itself is a countable set. It means that the equivalence class of every element is countable, and that if you have a bijection, a Borel bijection of X, or a partial subset of X, which lives inside, whose graph lives inside R, so it maps every point to an equivalent point, then it is measure preservable automatically. And basically, how this comes about, if you have a countable group action, countable group acting on X by probability preserving transformations, the orbit equivalence relation is measure-preserving equivalence relation, and vice versa. There's always a group in the background, but it's not unique, and so this is Feldman and Moore. And now, given a measurable f, define, given f and tau, which is measurable and satisfies that x, tau x is in the relation, almost surely. So I have a point which, a transformation, not injected, it lives inside. I can define f tau of x, which is kind of a formula that looks kind of like the Ruel operator. It's the sum over y is in the inverse image of tau, f of y. Okay, so it's kind of like, in a sense, it's the kind of the Ruel operator. F is not, so this, so what is, tau is not measure preserving, because it's not injecting. But, if I take f and I look at the integral of f, then it's integral the integral of f is equal to the integral of this transformed f. And what is this theorem and how is it related to the previous one? So really, because these countable equivalent relations always come from a group action, and because, for any group actions, okay, let me put it this way. So the point is that this tau gives you the point is that if I apply the theorem 1 for an A allocation with A equal x, the set A is equal to x, every function from x to gamma is an x allocation. The property is every measurable function. So if I do this, then I recover this theorem. Conversely, let's just look at the particular important, if I take f equal 1 in this theorem, and with this I conclude. So what does this formula tell you? This formula will tell me that if I look over x and I have a function tau, which preserves the relation, and I look at the expected pre-image of a point, it's equal to 1. Right, so this is a very basic fact. If you have a country and you have an elections, some people are up for election, others are not, and everyone can vote, must vote once. So the expected number of votes everyone gets is 1. Okay, so it's kind of very trivial in this sense, but somehow the fact that it's a countable measure preserving equivalence relation comes in, and if you weaken some of these assumptions, it fails. Okay, so I think I'm done.
Thank you very much. Are there any questions? Yes, please. I have 2 questions. So did I understand correctly that in theorem 2 you don't need x to be stamped?
In theorem 2, I don't need, it's enough, I don't need Borel structure or anything, yes. It's,
You don't need second component.
Yeah.
Okay, and the second question is, do you know if one can modify theorem 2 by assuming that, for example, the action is not using probability preserving, but maybe it's probability plus preserving, maybe with some bound on the Rodin derivative?
So of course, you're not assuming there's an absolutely but you're not assuming there's an absolutely continuous probability measure which is invariant. Yes. So I don't know. I mean, I think you would have to think a little for what formulation could make sense. But I mean, it's not. I mean, it uses measure preserving is used. I don't know what. I don't know. It's a good, interesting question, but the statement needs kind of to be. I mean, yeah.
No, you could.
I'm saying, do you think? I mean, the same statement, the same conclusion
Yes.
precisely. I don't think it holds if you
Okay.
just weaken it.
Okay.
If you look, let's say Z2, you have the lexicographic order. So if you take the minimum return time with respect to the lexicographic order, does it give you anything?
If you look at the minimum return time with respect to the lexicographical order, then
Of course, you can put two lexicographic orders depending on which one is first.
Let me think about this. I mean, it is. Yeah, I think that. Yeah, I need to think about.
You have to think about
Yeah, I need to
it.
think.
Okay.
Interesting question.
Okay. Are there any other questions? I see we have 1 more minute, so maybe I will ask a very simple question. If you take your formulation with annotation and say, I just want to see if I'm in the classical context, the Z action, do you get something surprising except the Katz lemma? So you showed us the example.
Yes,
I'm
yes,
asking if you can get something else.
Well, yeah, it gives you. I mean, you can get other allocations. Yeah, you get
Like
anything else.
something,
I mean, okay. So then you're asking, is it surprising, or what kind of applications you get from it? Yeah, that's a little. I mean, this does has an application. In the paper, we give an application, again, in the context of general groups or whatever, an application of this allocation machinery, and the application is the following result, which is, again, presumably not very surprising, but not sure there's a short proof in the literature, that if you have a countable group acting on probability space, there exists a countable generator, assuming, okay, so ergodicity is enough. The precise condition is that the number of atoms is at most countable. It's a necessary and sufficient condition for the existence of a countable generator. Okay, so yeah, it's a very soft result and it has a very easy proof. So whatever you prove, you can do by directly, but somehow it is basic.
Okay, great. So let's thank Tom again. We now have a break of 15 minutes, and our second talk starts at 12:30. Hello.